Hello everyone, welcome to my class. Now we start chapter 8, and in today's class I am going to cover section 8.1, systems of linear equations in two variables. So let me begin the class right away. First, let me give you an overview of chapter 8. In chapter 8, we study systems of linear equations and solving the system using the matrix method. First, we will investigate systems of linear equations in two variables, then systems of linear equations in three variables. Subsequently, we will focus on solving the systems of equations using matrix method, and we will finish the chapter 8 with solving the systems of equations using determinants and Cramer's rule. Note, linear equations means equations having variables to the first power, and a system of equations means a set of two or more equations consisting of two or more variables. Thus, a system of linear equations means a set of two or more linear equations. For example, this is a 2 by 2 system, so we have two equations and we have two unknowns. Here, number of equations is equal to the number of unknowns. Unknown means the variables here. So here, x and y are two unknowns or variables to be determined. The solution of the system, if exists, is the value of an ordered pair x, y of real numbers that solves both the equations in the system. In the above system, the ordered pair 2, -3 is a solution. We can verify immediately. Put x equals to 2 and y equals to -3. So this ordered pair satisfies both of these equations. So here x equals to 2, so 2 times 2 is 4, y equals to -3, so 4 minus 3 is 1. So we check the first equation is 2. Now for the second equations, put x equals to again 2 and y equals to -3. So this minus and minus is plus, so 2 plus 3 is 5, so 5 equals to 5. Check the second equations. Great. Let's begin sections 8.1, systems of linear equations in two variables. Definitions. A system of linear equations in two variables means a system consisting two linear equations in two variables. There are three types of systems of linear equations in two variables. First, we have an independent system where we have only one solution, that the intersection point is the solutions of the system. Second, we have a dependent systems where we have infinitely many solutions. That means two lines overlaps, means the lines represented by the equation of the systems overlaps. Third, the inconsistent systems where we have no solutions, the lines represented by the equation of the systems are parallel. So no intersection point here. And there are infinitely many intersection points, and there is only one intersection point. I hope this makes sense to you all. Method. There are graphical and algebraic methods of solving the systems of linear equations in two variables. So let's do example 1. Verify that the ordered pair is 3, 1 is a solution of the system. The system is 4x minus 3y equals to 9, 2x minus y equals to 5. So let's begin the solutions. So the idea is, let's plug x equals to 3 and y equals to 1 and verify these two equations. If it verifies, then this is a solution. If it does not verify, that means the given order pair is not a solution. So that's the idea. So begin the solutions. Let me scroll down this way. Yep. Substitute x equals to 3 and y equals to 1 in each equations. So here in the first equations, so 4x minus 3y equals to 9. Put x equals to 3, y equals to 1 in the next step. So here is a 4 times 3 minus 3 times y equals to 1. So equals to 9. And this implies 4 times 3 is 12 minus 3 times 1 is 3. So 12 minus 3 is 9. 9 equals to 9. It's true. That means the given order pair satisfies the first equation in the system. Now let's check for the second equations. Let me scroll down. Second equation is 2x minus y equals to 5. Again, put x equals to 3, y equals to 1. So in the next step, we have 2 times 3 minus 1 equals to 5. This implies 2 times 3 is 6, minus 1 is 5. So 5 equals to 5, 2. So that means given order pair 3, 1 also satisfies the second equations on the system. So that means the given order pair 3, 1 is the solutions to the given system. Great. I hope this idea makes sense to you all. Now let's move on. Let's take example 2. Solve the system of linear equations. The system is 2x plus y equals to 1, x minus y equals to 5. So we have two equations and two unknown. Using the following methods. Part A, solve the systems graphically. So let's graph the system using the slope-intercept form on the same plane. That means rewrite given equations as 2x plus y equals to 1 as y equals to minus 2x plus 1. Just isolate y alone to the left side. Similarly, x minus y equals to 5. Rewrite as y equals to x minus 5. So take y to the right, take 5 to the left. Now we have these equations here to graph. Then we can easily graph these linear equations. We can make either the xy tables, pick x values, find corresponding y and make an order pair and graph, or use this slope-intercept methods idea to graph those equations. Then now we have the graph here. So this blue graph is corresponds to this blue equation, so y equals to negative 2x plus 1, and this red graph corresponds to this red equations, y equals to x minus 5, and clearly the intersection point is here, which is 2 minus 3, 2 comma negative 3. Great. Since we have only one solution, so the system is, let me tell you, independent system. I hope this idea makes sense to you all. Now let's solve the systems using another methods. Part B, let's use substitutions method. Awesome. So let's do part B, substitution method. So in substitution methods, from one of the equations, write one variable in terms of the another variables and substitute that variables back to the another equations and solve. So for example, so here it's easier to rewrite the second equations for y variable. So let me write y equals to here x minus 5, then substitute that y equals to x minus 5 in the first equations. Then the first equation is 2x plus y equals to 1. So put y equals to x minus 5. Let me scroll down. Then 2x as it is plus y is x minus 5 equals to 1. Then solve for x. So here 2x plus x is 3x, and take minus 5 to the right hand side, it becomes plus 5 and plus 1 is 6. So we have 3x equals to 6. Divide both sides by 3, then we will have x equals to 2. So we found the value of x. Now put this value x equals to back in this equations here, then this gives us the y value. So here then y equals to x minus 5, put x equals to 2, we just found here. Then next step, this is 2 minus 5, which is minus 3, hence y equals to minus 3. That is x equals to 2 and y equals to minus 3. This is the solutions of the given system using the substitution method that we already knew using the graphical method. The solution is 2 comma minus 3. We are getting the same solutions but using different methods. I hope this idea makes sense to you all. Now let's move on. Next, let's do eliminations method. In elimination methods, we eliminate one variables and solve for the another variable. So here, let's eliminate the y variables. So given system is 2x plus y equals to 1, x minus y equals to 5. Just add these two equations, then y cancel out. So using r1 plus r2, that means row 1 plus row 2, means adding these two equations, then y cancels, then 2x plus x is 3x equals to 6. Divide both sides by 3, x equals to 2. Next, substitute x equals 2 in either of the original equations, is y equals to minus 3. If you put x equals to, let's say in the second equations, then x equals to 2, and 2 minus y equals to 5. Take y to the right, take 5 to the left, then 2 minus 5 is minus 3, y equals to minus 3. Hence, the solution of the system is the order pair 2, minus 3. Awesome. Now I hope it makes sense to you all. We solve the system using 3 different methods. First the graphical methods, then substitution method, then elimination methods. We got the same answer. Great. Now let's move on. Quick aside, the solutions we just found, that 2 minus 3 is consistent and independent. By the way, one can check to make sure that this is indeed the solutions to the system by plugging x equals to 2 and y equals to minus 3 in the systems. Quick note, the substitution method works best when a variable is easy to isolate or when one of the equations contains a coefficient of 1 or minus 1. Next, let's do example 3. Solve the systems and identify the system as consistent or inconsistent or dependent. So given systems is 0.2y equals to 0.3x plus 4 and 0.6x minus 0.4y equals to minus 1. Let's begin the solutions. Let's rearrange the equations here. So bring this 0.3x from first equation to the left, then we can rewrite as negative 0.3x plus 0.2y equals to 4, and from the second equations just copy down 0.6x minus 0.4y equals to minus 1. Then to eliminate the x, let's multiply the first equations by 2 and add to the second equation. So here, that this operations 2 times row 1 plus row 2, then multiplying by 2 both sides to the first equations becomes minus 0.6x plus 0.4y equals to 8. And the second equation as it is 0.6x minus 0.4y equals to minus 1. Add these two equations. X terms cancel out, y terms cancel out, then we have left side 0 and on our right side 8 minus 1 is 7, but this is not true, right? 0 is not equals to 7. Hence the system has no solutions and the system is inconsistent. That means these two lines are parallel lines. So let me show you the graph earlier. So now we have these conditions here, no solutions, the third conditions. Great. Let me scroll down again. Now let's do another example. Example 4, applications problem. At a recent production of a comedy of errors, the community theater brought in a total of $30,495 in revenue. If adult tickets were $9 and the child tickets were $6.50, how many tickets of each type were sold if 3,800 tickets in all were sold. I hope the question makes sense to you all. So now to do the application type problem, label all variables and set up a system of equations. Please do not apply trial and error methods. So let's begin the solutions here. So what are the unknowns here? The unknowns are adult tickets and child tickets. So let's assume X represents the number of adult tickets sold and Y represents the number of child tickets sold. Then let's write the systems here. So total tickets were 3,800. So that means X plus Y is 3,800. That's the one equation. Then another equation is X is the adult ticket. So here is a $9 for each adult ticket. That means 9 times X plus Y represents the child tickets, and each child ticket cost $6.50. So the total is 6.5 Y, and the total revenue equals to 30,495. So now we have a systems here. I hope this conversion makes sense to you all. Two equations, two unknowns. Now we can solve the system. Let's follow the substitution technique. Then from the first equations, write X equals to, in terms of Y, which is 3,800 minus Y. Then substitute it into the second equation. The second equation is 9X plus 6.5Y equals to 30,495. Next step, 9 as it is, X equals to 38,000 minus Y plus 6.5Y equals to 30,495. Now let's solve for Y. So next, FOIL this product here, send 9 to inside. So 9 times 3800 minus 9 times Y plus 6.5Y equals to 30,495. Right inside as it is. Next step, here minus 9Y plus 6.5Y equals to minus 2.5Y, then equals to, right inside as it is, and take this constant to the right hand side, so it becomes a minus here. So we have on our right hand side 30,495 minus 9 times 3,800. Great. Then simplify. The constant on our right hand side is equal to minus 3,705, and divide both sides by minus 2.5, then Y turns out to be 1,482. So next, let's substitute Y equals to this value 1,482 in the first equations, maybe here. Then X turns out to be 2,318. Hence X represents the adult tickets, Y represents the child tickets. So the total adult tickets sold were 2,318. Similarly, the total child tickets sold were 1,482. Great. So we finished these sections. Maybe that's better. Yeah, we finished these sections. Thank you.